All right. Welcome, everyone. So every year when I teach Paradox and Infinity, I wish I knew more physics so that I could talk about time travel in the context of contemporary physics. But this year, there's something much better. It's a dream come true. So this year, Alan Guth from the physics department has graciously agreed to come talk to us about time travel in the context of contemporary physics. Probably all of you have heard of him, but he's not only a beloved MIT professor, but also the person who first proposed cosmic inflation, amongst many other cool things. So welcome, and thank you so much for being here.
Thank you. Okay, so time travel is certainly a fun topic, so I think we all should have fun today. Do feel free to break in and ask questions anytime you feel like it, because I don't really know exactly what your backgrounds are, so I may or may not make contact the first time, but I'll keep trying. So do, by all means, ask questions whenever a question occurs to you. The class is certainly small enough to make that possible. So that said, what I'd like to go on to talk about is something which is, I think, a lot of fun because it really can be done in a rather simple way. I'd like to discuss a particular time machine invented by Richard Gott of Princeton, which shows how peculiar things in general relativity can perhaps lead to closed time-like curves, which is sort of the technical word for time travel. The point is that in special relativity, space-time is rigid and really does not provide for time travel. In a Minkowski space, you can only go in your forward light cone. That is, in the space-time of special relativity, you can only move in your forward light cone. And that means you can never turn around and go back and come back to earlier times. But general relativity is different and makes everything much more complicated. In general relativity, space-time itself is plastic. It's dynamical. It can bend, twist, stretch, do all kinds of things. And that opens the question of whether or not space-time could become so distorted that you could travel in a direction which always appears locally to look like it's forward in time, but you still end up back somewhere in the past because of the way the space-time has twisted itself up. If you're back in the past, you could then go forward in time and get back to where you started. And that's usually how it's discussed, because it's a simple thing to talk about. So one talks in general relativity about the possibility of a closed time-like curve, which means a curve which everywhere looks like it's time-like, looks like you're moving into the future, but you end up back where you started from, which means that immediately before you end up there, you were really in the past of where you started from. So it really is time travel. So the question is, can you produce things like this? Now, the equations of general relativity actually imply very little on their own. I won't get into writing the equations down even. What the equations of general relativity do for you is they give you a relationship between properties of the space-time and properties of the matter that is producing the gravitational field, and hence the distortion of that space-time. And the space-time itself can do anything if you have matter that fits the other side of the equation. So any restriction in general relativity about what a space-time can do really boils down to restrictions on what matter can do. And the catch in terms of deciding whether or not general relativity can produce closed time-like curves depends on what it is you assume about the matter in the universe. With the strongest theorem that I know of is still very weak, really, as far as excluding closed time-like curves. The strongest theorem that I know of says that if you assume that matter obeys a certain condition called the weak energy condition, which is actually known not to really hold for quantum matter, but it holds on average, but it doesn't really hold locally. Then you can prove that if you don't have closed time-like curves, you cannot produce them unless you produce a singularity, which is also an important catch because black holes do form singularities. So the bottom line is that very little can be proven about the absence of closed time-like curves in general relativity. And what I'll be showing you is a construction of a system which actually entails a closed time-like curve. It does not actually produce the closed time-like curve, however. The closed time-like curve is really always there if you have this system. So it can't quite be described as the production of a closed time-like curve. So the construction was created by Richard Gott in 1991. Maybe I should give you a reference to the paper, which I happen to have brought with me. The title of the paper, which I won't write on the board because it's a bit long, is Closed Time-like Curves Produced by Pairs of Moving Cosmic Strings, Exact Solutions. That's Richard Gott. Phys Rev Letters, volume 66, page 1126, 1991. And this, by the way, is something which, after this paper was written, I worked on this construction, on some properties of this construction, with one of the professors who's still here, Eddie Farhi, and also Sean Carroll, who's now at Caltech, and Ken Olam, who's now at Tufts. And maybe at the end I'll tell you about what questions we asked and what answers we got, which are interesting, and actually do reflect on the question of whether or not closed time-like curves are really possible. We basically concluded for the time that it looked like they were possible, but then it turned out we missed something important, and the way of creating them that we had in mind turned out not to work, which led us all, I think personally, to reach the conclusion at the end that it looks like nature really is somehow trying hard to conspire to prevent closed time-like curves from happening. And this has nothing to do with the grandfather paradox, just the dynamics of these systems. And I hope we'll have time to tell you more detail about that at the end, but the questions will make much more sense later. Okay, I need to say at the beginning some things about the context of this Gott time machine. The Gott time machine, as you may have heard in the title if you were listening, has to do with moving cosmic strings. So I'll tell you what a cosmic string is, more or less. A cosmic string is not an object that anybody has ever seen in nature, but an object which theoretically exists in some but not all theories. And by some but not all theories, I'm talking about extensions of the standard model of particle physics. The standard model of particle physics does not produce strings, cosmic strings, but other theories do. And theories that are plausible extensions of the standard model can lead to these things called cosmic strings. An interesting feature of these cosmic strings is that they do not violate this weak energy condition, which is sometimes used as a criterion for exotic matter. If you can violate the weak energy condition, there are other kinds of time machines that you can build in a fairly straightforward way. So this is all consistent with the weak energy condition, which makes it in some ways more plausible than other kinds of time machines. When do cosmic strings happen? What are they? Cosmic strings are configurations of fields that can exist in some kinds of theories. And to make a cosmic string, what you want to have is a pair of scalar fields, two scalar fields. And I will call them phi sub 1 and phi sub 2. For some reason, particle physics always calls scalar fields phi, so it'll be called phi. Now, to clarify what I mean by a field, for those of you who might not be in on these things, you are all, I assume, familiar with electric and magnetic fields. And I assume you're also all familiar with the idea that a bundle of energy of the electromagnetic field acts like a particle, and it's called a photon. So the way that shapes up theoretically is one can start with Maxwell's equations describing the electric and magnetic fields, and then one can, quote, quantize that system, which means really to exercise a fairly standard set of rules which develops a quantum system that corresponds to any given classical system. And when you do that for the electromagnetic field, one feature of that quantum theory is that unlike the classical theory, in the quantum theory, energy only comes in discrete bundles. You can't have any old energy. You can only have energies in certain bundles, certain quanta of energy. And those bundles of energy are the photons. Now, it turns out, and this is something that's known to probably some of you, but not all, that by far the easiest way, perhaps even the only way that we know of, to describe relativistic interacting quantum particles is to describe them in the same way that we describe photons. That is, we invent a field for the electron, for the quarks, for all the particles of the standard model of particle physics. For each particle, we invent a field, and we treat the particle as simply the quantized excitation of that field. That is a bundle of energy of the field, just as the photon is a bundle of energy of the electromagnetic field. So particle physicists are used to dealing with fields all the time, and now we even know what a scalar field is in nature. A scalar field, by the way, just means a field which does not pick out any direction, like the electric field, which is a vector. A scalar field is just a number defined at each point in space. And when you quantize it, the particles that are described by that scalar field have no angular momentum. That's what characterizes their scalarness. And we now know of one example that we've actually seen, namely the Higgs particle that you probably heard a lot about the summer before last when it was discovered at CERN. And it was predicted probably, I forget, 40 years earlier or 50 years earlier, I forget. Predicted a long time ago. So scalar fields do exist, and scalar fields are just the ingredients that you need to build a cosmic string. So what we want to have to build our cosmic string is two scalar fields, and we want a potential energy function, which in general is a function of the two fields, but we're going to insist that it actually be a function only of the magnitude of phi vector, where phi vector is just the two fields thought of as one field. It's thought of as an ordered pair of fields. So the magnitude of phi vector is just really an abbreviation for the square root of phi 1 squared plus phi 2 squared. And this means that the potential energy function, at least, and in fact the entire theory, is symmetric under making rotations in the phi 1, phi 2 plane. You can mix phi 1 and phi 2 arbitrarily. And as long as you keep phi 1 squared plus phi 2 squared fixed, the energy is the same, and really all the physical properties are the same. OK, now we have to make up something for V to look like. And the kind of V that gives cosmic strings, in fact, is the same kind of V in qualitative form that the Higgs field has. It's a little peculiar if you haven't seen this. But the potential energy function has the property that instead of vanishing when there's no field, I should maybe mention for reference that for the electric field, many of you probably know that the equivalent formula here is just to say that the energy density of an electric field is some constant that depends on your units times the square of the electric field. So the energy density of the electric field vanishes when the electric field vanishes, which makes a lot of common sense. This scalar field we're going to assume is different from that. We're going to assume that for zero field it has some non-zero positive energy density, and at some non-zero value for the magnitude of phi, the energy density goes to 0 and then goes up again. And this is, in fact, exactly what's assumed for the Higgs field of the standard model, the one that actually now has been verified at CERN. So this can happen, and now we even think we verified it does happen. It's certainly peculiar that the energy density is non-zero and the field is 0, but nothing prevents that. OK, now what does this do for us? It gives us and this is the same for the Higgs particle, it gives us a degenerate vacuum. That is, the vacuum is not unique, but there's a class of vacuum states. Any state for which the magnitude of phi is equal to this value, we can call this phi sub v for vacuum. Any combination of phi 1 and phi 2, which gives us the right phi sub v, will have zero energy density and will be a possible minimum of the system, minimum energy state of the system. So the minimum energy state is not unique anymore, as it usually is assumed to be. And that offers a peculiar possibility, which I will now draw for you. And this will be the cosmic string. The picture about to appear here will be the cosmic string we are looking for. So this cosmic string I'm going to draw will be coming straight out of the blackboard, and we'll go on to infinity. And that's actually the simplest thing to use. You need infinite cosmic strings to build the Scott time machine, which makes it a little bit artificial. And this is exactly what we're going to use to build the Scott time machine. So it'll be an infinite string going out of the blackboard and into the blackboard. It depends only on the coordinates x and y and not z, where z is the coordinate coming out of the blackboard. And what I want to do is to draw this pictorially. I don't want to write an equation. And the equation actually is variable depending on the exact form of the potential. So it's not even significant to write an equation. To draw our doublet of fields, phi 1 and phi 2, I'm going to draw this as a vector, as if it were phi 1 times I hat plus phi 2 times j hat. It's just a two-dimensional vector. And in principle, the field is described by drawing a two-dimensional vector at every point in this diagram. I won't draw it at every point because that gets a bit hard, but I'll draw a representative point so that you can fill in the gaps mentally. At the center, the field is going to vanish. So the vector is just a null vector at point. Slightly away from this two-dimensional vector is going to be a vector that points radially outward. And for continuity, the vector will get shorter and shorter as we consider locations closer and closer to the origin. So the field will look like that for very nearby points. These arrows will get a little longer for points further away. And I might draw more points to make it more suggestive of what's really happening. All points at the same radius are supposed to be the same length. So magnitude of the vector depends only on the magnitude of the distance from the origin. And then at large distances, these arrows will be at the vacuum length. So there's no more energy density at large distances. All of the energy is concentrated in the vicinity of the origin. So this shaded region is the region with non-zero energy density. The energy density might only approach zero at large distances. It may not ever actually equal zero, but it approaches zero quickly. So the potential energy converges. Now, an important, at least a relevant feature of this diagram, which really won't be important for what we're doing, but it's important for other reasons, I'll mention it anyway, is that this configuration is what is called topologically stable. And what that means is that if you were to freeze just the direction of these arrows at infinity, or on any large circle, it doesn't really have to be infinitely far away, then if you insisted that the field be continuous, no matter how you varied it, there would always be a point where the vector vanishes. It's similar to the theorem about combing hair on spheres and things like that. And I'm not going to try to prove it, but you can sort of visualize it if you imagine varying this. There's not really any way you can vary it continuously and make the zero disappear. So the zero defines the center of the cosmic string. It means cosmic strings cannot disappear for topological reasons. Okay, but we, in any case, are only going to consider an infinitely long straight cosmic string which doesn't do anything. So we don't really have to worry if it could disappear. It's certainly not going to if we don't do anything to it. And we're not going to, really. So this is our cosmic string. There's one more catch, which I'll just mention, which is that there's a term in the full energy density, besides this potential energy density, there's a term proportional to the gradient of the field squared, which contributes to the energy density of a field. And if you work out what that is, you'll discover that it actually would give a divergent contribution here. It would diverge at large distances. The gradient itself would fall off like 1 over the distance. The gradient squared would then fall off like 1 over the square of the distance. But then if you integrate that over the area, we're talking about the energy per area here. It's infinitely long, but we're trying to calculate the energy per area. So we'd integrate that over the area, and that would give us an integral of r dr divided by r squared, where the 1 over r squared was the energy density itself. And that would give us an integral dr over r, which would diverge logarithmically at large distances. So that does not happen for quote, real cosmic strings, meaning the ones that really exist in our theories. And the extra ingredient that prevents that from happening is an interaction term that allows the scalar fields to interact with what in this case could be the ordinary electromagnetic field. And there's a way of putting in an interaction, which I won't show you, where you could arrange for that interaction to cancel the infinite energy that you would get if you just had the scalar field and nothing else. Okay, not important for us, though. What's important for us is now that we see that this thing is at least something we can talk about, what does it do to general relativity? What happens when we try to put an object like this in general relativity and ask what does it do to the space-time? And it does a very simple and very peculiar thing. It turns out that the space-time that it creates is a little complicated if we deal with the central region where the non-zero energy density is. So we're not going to worry about that. We're going to imagine it's very thin, which in fact it is. It's submicroscopic in thickness for a realistic theory. So we're going to neglect the size of this and talk about what happens in the region where there's no energy density anymore, but we just have this energy at the core. And it turns out that a cosmic string produces no local perturbation in the space except at the core. But it does produce instead a deficit angle. That is the total circumference of a circle that I would draw here would be consistently less than 2 pi times the distance from the origin. Now, the way to think about that and I bought some toys, which I'll show you in a second to help illustrate this. The way to think about that is to imagine a disk, which is in the same two-dimensional xy space that we're talking about there. I could have drawn on top of that, but it would get hard to see. And the space looks like a perfectly Euclidean disk, except that there's an angle cut out called the deficit angle, and often called by the Greek letter alpha. And this space inside the deficit angle just doesn't exist. The only points that exist are the points outside the deficit angle. And this line is identified with that line. So if we were to travel in this space, when we went into the deficit angle here, we'd immediately appear on the opposite side there. And this can be constructed out of paper. So I just happened to have brought with me a disk, plain ordinary disk, nothing up my sleeves and all that. But there's a deficit angle marked, a pi slice. And what I'm going to do is imagine that we actually remove that deficit angle, because there's not supposed to be any space inside this deficit angle. So I will cut it out with my scissor. Voila. And now we want to identify this line with this line, which we can do by physically joining them together, like yay. And to the extent that I did this well, what we have is just an ordinary cone. It's a somewhat surprising fact, at least I find it surprising, that the surface of a cone actually is just a flat piece of paper curled up. Notice I cannot do this with a sphere. If If I were to try to make a sphere, I'd have to make zillions of cuts and sandwich them together to get the curvature of the sphere. But the surface of a cone actually has no curvature at all. The surface of a cone really is just a perfectly flat surface, but curled up with a deficit angle. So that if we were to talk about the distance all the way around at some radius from the center, the distance all the way around, the circumference would be less than 2 pi times the radius, less than by the amount that we cut out here. So this is the surface. This surface is the two-dimensional surface of a cross-section of the cosmic string. Something which I think I should point out, so I'll do it. I can make this identification more sturdy by using a little Scotch tape. So I'm going to do that. Okay, and I like to imagine that I Scotch taped it together so well that it's completely seamless. There is a seam there because Scotch tape looks like Scotch tape. But if we imagine that I could sort of weave the paper together, we could imagine removing the seam completely and just have a seamless cone. And the point that I wanted to add to what I said already is that if we imagine that we have a seamless cone, I can flatten it out by cutting it anywhere. I don't have to cut it where the original cut was. If I cut it someplace else, I again get a flat piece of paper with a deficit angle cut out. So the moral of that is that you never really know where the deficit angle is. The deficit angle is really just a tool that's useful for us to be able to flatten the cone. As long as we thought of the cone as a cone, we wouldn't need the deficit angle at all. And if we want to flatten it out just to make it easier to draw, it's easier to draw a flat surface than to draw a cone in perspective. And we'll be doing that. We'll be drawing the flat surface version of the cone. We can cut the deficit angle anywhere we want, and we'll get the same cone. The piece of paper is the same no matter where I made that cut to flatten it. OK? OK. So what does this mean about the physics of a cosmic string? One of the things it means is that if there were a cosmic string here coming up the floor and going up to the ceiling, no matter how massive that cosmic string was, I could stand right next to it, and I don't feel any gravitational attraction at all. Because locally, the space-time is really just not deformed in the least. And gravitational fields are just manifestations of distortions of space-time, which is what general relativity usually does. But for the cosmic string, there's none of it. It produces no local distortion of the space-time. But if there was a cosmic string here, I could learn about that cosmic string one way to walk around it and measure the circumference of my circle and measure the radius and discover that they don't match the way they should in Euclidean space. In a similar vein, if you think about what light would look like if I had a light bulb behind the cosmic string, it would actually look double to me because there would be paths that the light could travel on both sides of the apex of the cone, on both sides of the cosmic string, and still reach my eye. So you would see it in double images. And people have, in fact, astronomically looked for double images on the sky to see if we see any signs of cosmic strings. And there were a few candidates discovered, and there was a bit of a hullabaloo for a little while, but there was never anything definitive enough for anybody to believe it. So we have not seen cosmic strings, but people are still looking. OK, now how are we going to use this to build a time machine? Let's start on that. Oh, I should mention one thing maybe. How to relate this deficit angle to the mass per length of the string. What general relativity implies is that alpha is equal to 8 pi times Newton's constant times mu, where mu is the mass per length of the string. Just to make it concrete. OK, so how do we build a time machine? What I want to do next is to consider a space with a cosmic string. And it will again be a cosmic string coming out of the blackboard. So that dot is our cosmic string. Might just mention, for the sake of interest, that if we have nothing in our system except cosmic strings, which are all coming straight out of the blackboard, every cosmic string will look like a dot in the blackboard. And we could just as well forget about the z direction, where nothing happens in the z direction, and just think of it as a two-space dimension theory with point particles instead of cosmic strings. And particle physicists like to think about things in different dimensions. So most particle physicists would prefer to think about this actually as a two-dimensional system of point particles rather than a three-dimensional system of infinitely long cosmic strings. But they're equivalent, so you could think about it either way. So we have a cosmic, I'll use the cosmic string language. We have a cosmic string coming out of the blackboard there, creating a deficit angle in our picture. I'm going to draw the deficit angle upward in our picture. So that deficit angle describes how the cosmic string has distorted the space. There's no space inside this deficit angle, only space out here. Anything that goes in there instantly comes out there at exactly the same instant of time, because these points are really the same point. OK, now what I want to do is to draw underneath this a horizontal axis, which I will call the x-axis. And want to think about 2 points on each side of the cosmic string. We can make them equally spaced to make things simple. They don't have to be, but they might as well be. We're just trying to show the existence of this thing. And what I want to do is to imagine light rays that might travel from A to B. And as I mentioned when I was talking about seeing double images, in this picture we'll be able to see the double image very explicitly. A light ray can get from A to B along a, quote, straight line 2 different ways. One way is the obvious way of going straight across the horizontal from there to there. But it's also a straight line if the light ray comes perpendicular to the deficit angle, leaves perpendicular on the other side instantly, jumping from there to there. It can come back to B this way. That's also a straight line from A to B. And if we put it back together as a cone, these two would look equivalent to each other. They both look like straight lines drawn on the surface of the cone. The only difference is that this one has been split by the deficit angle by cutting it with the scissors. OK, now, I don't think I've really drawn it quite the way I would have wanted to, as far as getting the proportions right. But there are ways to arrange this. If I make this very close to this, it will always happen. There are ways to arrange this so that the path that goes through the deficit angle is shorter than the straight line path from A to B across the horizontal. And the easiest way to really convince yourself that that's always possible is that if you first drew it and it didn't turn out that way, you could always imagine drawing this on a piece of paper, cementing this to this, putting in a deficit angle this way, and then this will be the one that goes through the deficit angle instead of the one above. And one of them is always shorter, unless you've got them to be exactly equal. So you could always, by choice, arrange for the shorter one to be the one that goes through the deficit angle, which is what I want to do. OK, now, given this situation, I now would like to think about something, slight modification. I want to compare a light ray that goes from A to B on the horizontal with a high-speed rocket, which goes near the speed of light, but rockets always go a little bit less than the speed of light. But that's OK. We'll let it go a little bit less than the speed of light. But the rocket's going to take the shortcut path through the deficit angle. Okay. If the rocket is going fast enough, it can get to B before the light ray. This is traveling on a shorter path, and we're going to allow it to go arbitrarily close to, but not quite equal to, the speed of light. So if it went the speed of light, it would certainly get to B first, because we said it's a shorter path. If it goes ever so slightly less than the speed of light, it could still get to B ahead of the light ray. And that is sort of the quintessential secret of traveling backwards in time, to be able to go faster than light in some sense. And this, in some sense, is going faster than light. Of course, locally, it's never going faster than light. It's just found a shortcut, allowing it to beat a light ray. Okay, so the diagram I just drew is just a picture of the thing in space. Now what I'd like to draw is a space-time diagram of sorts, where my x-axis is my x-axis. I'm going to only consider points that are on the x-axis for drawing this diagram, because I don't want to try to draw a three-dimensional diagram. I want to add time. So that's OK. All I'm really going to be interested in is points along the x-axis. So I'm going to use the x-axis and time, and just y will be 0 for everything that I'm drawing. So we need to draw y. So x is that way, t is that way. We can draw where a and b are. A moves through time. It's static, and so is b. So these dotted lines represent a and b evolving in time. I can now draw what happens to our light ray and our rocket. The light ray moves along the x-axis, and if I scale x and t in the right relativistic way, relating them by the speed of light, the light-like line will just be a 45-degree line, measuring time in light years, for example. It moves 1 light year per year. So the speed is 1 in the right units. So this is our light ray. Now, the rocket ship is not going to stay on the x-axis. So it will start at the same place in time as the light ray. That will be the origin of our rocket. It will leave this picture because it will go to other values of y that we're not trying to draw, where it can go around this deficit angle. But it will arrive the same place. It will come back to the x-axis, traveling along the path shown there. And it will get to B before the light ray. I'll put a point here, which I'll call B sub rock for rocket. This is where the rocket ends up after its trip. So light ray here, rocket there, which means the rocket has gone from here to here. If we don't worry about what it did in between, it has clearly effectively traveled faster than light, as far as this diagram is concerned, as far as the starting point and ending point, for ignoring what happened in between. And now, to turn this into a time machine, I want to use a fact about special relativity, which I won't try to show, but I imagine a lot of you know, which is that if 2 points in a space-time diagram are related to each other by an effective speed which is faster than that of light, that's called a space-like separation, if you're familiar with this lingo. If 2 points are space-like separated, you can always boost, that is, change your velocity to go to a reference frame where those 2 points are simultaneous. That's the relativity of simultaneity. Points which are simultaneous to one observer do not look simultaneous to another. And the criterion for their existing a frame where they are simultaneous is that in any frame they are space-like separated. That is, they're separated so that you can only get from one event to the other by traveling faster than the speed of light. Okay, but that's the case here. So using this fact about special relativity, which you may or may not know, just for curiosity, how many of you know that fact? OK, looks like about half. OK, the rest of you believe it. And you can ask a friend. So we're going to use that fact. We're going to go to a moving frame. And the velocity of this moving frame has to be just right to make these 2 particular points simultaneous. But in our moving frame, which I will draw as x prime, t prime, I will call the coordinates of the moving frame. In the x prime, t prime coordinate system, A and B, or A and B rock, will be simultaneous. In this moving frame, the rocket will appear to have landed at the same time it took off, but at a distant place. Now, this certainly looks like you have something like the makings of a time machine. You managed to get from here to there in no time at all. But it's not quite a time machine yet, because time in general relativity is defined locally, which is sort of the way time is defined on Earth. So as far as what we've really shown so far, what we have is sort of similar to taking off in New York and landing in California at the same time on the clock. And that's possible because the times on the clock have offsets. And in general relativity, you can never even exactly tell when there is an offset and when there isn't, because there's no definitive way of defining what simultaneity means. So in our coordinate system, it lands at the same time it took off, but that's not yet a closed time-like curve. I can draw you in a little bit more detail what this looks like before we go on, and then we'll complete the story. Might as well stay on the center boards, and I can draw over there. Okay, that is the space-time picture. I can now sort of draw what it looks like in space without trying to draw time on the same axes. In space, we have an x prime axis. There will actually be a y prime axis perpendicular to it. I'm drawing the 2 dimensions of space in our moving frame. There will be a deficit angle here because we're trying to draw this conical space on a flat diagram. So the cosmic string will be somewhere. We'll put the cosmic string there, and we'll put its deficit angle again up. There's the deficit angle. Since we've gone to a moving frame, in our new frame, the cosmic string will not be stationary. I could draw the instant where it's at x equals 0, or x prime equals 0, but it will be moving. And to get this to work, the direction of motion is to the left. So instead of having a cosmic string at rest, now we have a cosmic string that's moving. And our rocket is going to be taking off there and landing there. And it will do it by traveling around the cosmic string in some way. This is only meant to be schematic, that picture, but it describes what the path does. It goes around the cosmic string and comes back. And it lands in this frame at the same time as it took off. Now, what we'd like to do to complete a closed time-like curve, which is the unambiguous definition of a time machine, which does not depend on any choices of coordinates. This simultaneity clearly did depend on our choice of coordinates. We were able to make it, which was itself surprising, but it's still a coordinate-dependent statement. What we'd like to do is somehow get back, and get back to A at the same time as we left. And that would be what the general relativists would call a closed time-like curve, which is a real time machine. If we went back along the same path, we'd be passing the cosmic string in the opposite direction. Here we're moving against the cosmic string, which was really essential to be able to land at the same time. If we went back, because we'd be going in the same direction as the cosmic string, it would really just reverse itself. And the amount of time it would take to get back to A would be the total amount of time for the trip, which would be certainly positive, not 0. But what got realized is something which may or may not be obvious to you. Once you draw the right pictures, it's almost obvious. Do any of you see how I can get back at 0 time? Yes? Put another one underneath. Exactly. Right. There's nothing that stops us. There's emptiness here, just empty space. We can do whatever we want with it. We can put a second cosmic string here and let it go that way with the same speed. And now, once we get to here, we can come back by going around the other cosmic string. And now we're again going against it. What's happening in the bottom half of the picture on the return trip is exactly what happened on the top half of the picture on the going trip. And now we have a return trip, which reproduces the simultaneity effect. The rocket will land back at A at exactly the same time as it took off. So this space-time has, in a very simple way, a closed time-like curve. So having said that, I think I have a few minutes left. I have a minute and a half left. I will quickly summarize what Eddie Farhi and Sean Carroll and Ken Olam and I learned where we tried to study some features of this solution. We first asked ourselves the question of, suppose we didn't actually start out with these moving cosmic strings. Suppose we just started out with a configuration of cosmic strings. Let me call them particles now and think of this two-dimensional picture. This, what I'm talking about makes more sense in that language. Suppose we started out with particles at rest. and tried to create a got time machine by having the particles decay. And when two particles decay, two halves can shoot out in opposite directions. And you could then use those shooting particles to cross each other. You start out with two particles here and here, have this one decay into a pair that way, this one decay into a pair that way. You're going to have two cosmic strings passing each other. Can those two cosmic strings that pass each other make a closed time-like curve? That was the question we asked. What we discovered is that no matter how you arrange the parameters, you could never have enough energy in a two-dimensional open universe, let's call it, one that just goes on to infinity, to make a got pair that way. Just not possible. Notice that in these funny two-dimensional universes with got-type particles, cosmic strain-type particles, there is a maximum total energy you can have, because the deficit angle can't be bigger than 2 pi. And that maximum killed you here. But we realized that you don't have to have an open universe, one that just goes on, which has a limit of 2 pi for the deficit angle. You can have a closed universe, one where the surface makes a closed figure. And the simplest closed figure is just a cube. And if you look at the total deficit angle of a cube, adding up what you get for each of the 8 corners, the total deficit angle of a cube is actually 4 pi, not 2 pi. So you have more total energy available if you start with a closed universe instead of an open one. And we discovered that with our closed universe, we could arrange it so that when particles decayed, they shoot particles at each other at a speed which would exceed this threshold to make a time machine. And we could produce a got pair at this supercritical velocity. There's a minimum velocity needed for our rocket ship. We said it had to be near the speed of light to make this work. How near depends on how big the deficit angle is. But we discovered that we could do that. We could, starting out with this rectangular solid or square or cube, we could send particles at each other fast enough so it looks like it should build a got time machine. And we thought, oh, great, we figured out how to actually make a time machine. And we added this to a footnote, the footnote to the paper that we were writing saying that for the open universe you could not do it. We added this footnote saying that for the closed universe you can. But turned out we were wrong. Time machines are tricky. And the person who proved us wrong was Gerard de Tufte, who later won the Nobel Prize, not for this, but for other work. Smart guy. What he did is to look more carefully at our construction. And what he found was the rather shocking fact that even though the particles were coming at each other fast enough so that you could, if you knew nothing else, imagine going around those two particles and making a closed time-like curve. But this time we have a closed universe to start with, not an open one. And closed universes can collapse. And what Tufte discovered is that in all cases, he developed a proof, the universe would collapse before there was time for anything to go around a closed time-like curve, which means the closed time-like curve doesn't really exist. And it's an effect that seems like it's totally out of the blue in that it doesn't have anything to do with any of the properties that we've used so far to construct the time machine. So that's what I mentioned at the beginning of my talk, gave the feeling to at least Eddie Farhi and me that somehow nature tries very hard to conspire to prevent closed time-like curves from happening in ways that I think we still don't fully understand. And I will stop there. But if any questions, I would be glad to ask them, glad to answer them. Time machine syndrome. OK, well, I can stay around for a few minutes if any of you have questions in private.
Thank you so much.